A rapidly emerging PV technology is that of perovskite solar cells. Perovskites have seen a tremendous increase in initial efficiency in the recent years. Perovskite cells with 2.2% were reported in 2006. Cells with an efficiency of 6.5 were reported in 2011, and since then the reported efficiencies have rapidly increased with an actual certified record efficiency of 19.7%. Non-certified cell efficiencies higher than 22% have been reported as well in literature. The objective of this video lecture is to get familiar with the material and lattice properties of photovoltaic materials based on halide perovskites. Secondly, we will discuss the most important device structures and the operation mechanisms of the perovskite PV devices. Thirdly, we will discuss the challenges this emerging PV technology is still facing, including some of the approaches to tackle these challenges. What are perovskites? Perovskites are minerals with the general formula AbX3, where X is an anion and both A and B are cations. An anion is a negatively charged ion, whereas a cation is a positively charged ion. The mineral perovskites with the formula of calcium titanium oxide is named after the Russian mineralogist A. Perovsky, who lived from 1792 to 1856. The figure illustrates the general cubic crystal structure of the perovskites AbX3. For photovoltaics, organic inorganic perovskites are used where the large cation A is organic. Often methyl ammonium CH3NH3, abbreviated with Ma, is used, or formamidinium CHNH22, abbreviated with Fa, is used. X is an halogen, such as iodine, chlorine, or bromide. Often these mixed halide materials are used. The cation B usually contains lead, while tin can also be used. The halide perovskite materials have received extensive attentions in the PV research due to its promising physical properties. Let's discuss some properties. Based on absorption measurements and simulation results, it can be concluded that the halide perovskite solar cells have a material based on a direct band gap. Here we see a typical absorption spectrum of a methyl ammonium lead iodide perovskite material. It has a relatively sharp band gap. Let's include the absorption characteristic of the gallium arsenide. Gallium arsenide is a direct band gap material and therefore has a sharp band gap. We can see that the band gap of the perovskites is not that sharp, but methyl ammonium lead iodide material is getting pretty close. If we add the absorption coefficient of crystalline silicon to the graph, we can see a clear difference. Crystalline silicon is an indirect band gap material above the 400 nanometers and has a significant lower absorption coefficient. In contrast, the direct band gap properties of the methyl ammonium lead iodide result in a high absorption coefficients in the visible part. These absorption characteristics make the material suitable to be used as thin film PV material. Secondly, methyl ammonium lead iodide has a much sharper band gap when compared to crystalline silicon. The electrical properties are highly interesting as well. The perovskite material does not have a field-dependent exciton dissociation. Also, due to its defect tolerance, the low trap densities in the bulk results in a long intrinsic diffusion length and relatively long carrier recombination lifetimes. The band gap can be tuned by the Loy and can range from 1.3 up to 2.3 electron volts. The standard methyl ammonium lead iodide perovskite has a band gap of 1.55 electron volt or 800 nanometers expressed in wavelengths. The halogen anion X or iodine can, for instance, be replaced by bromine. The band gap of methyl ammonium lead bromide shifts to higher energies up into the visible range. It has a band gap of 2.3 electron volt as a wavelength of 539 nanometers. In reference to the standard methyl ammonium lead iodide perovskite, the cation based on the 4-valence element, in this case lead, can be replaced by the 4-valence element like tin. the band gap of metal ammonium tin iodide shifts to the infrared. It has a band gap of 1.3 electron volt or 954 nanometers expressed in wavelengths. The organic cation metal ammonium CH3NH3 can also be replaced by formamidinium CHNH2 This has a minor effect on the band gap in reference to metal ammonium lead iodide. The band gap of formamidinium metal ammonium lead iodide has a small redshift. Its value is in the order of 1.5 electron volts, which corresponds to the wavelength of 827 nanometers. Of course, band gaps can be tuned using mixtures of these different halide perovskites. For instance, for high-bright tandem applications, higher band gaps than that of the metal ammonium lead iodide are required. Such applications require halide perovskite material based on a mixture of metal ammonium lead iodide and metal ammonium lead bromide. Perovskites can be deposited using several processing methods. Various deposition technologies can result in high-quality perovskite films. The method most explored is solution-based crystallization using spin coating of a precursor solution. Processing has been further developed and post-treatments have been successfully applied in which anti-solvents of the ethyl ammonium lead iodide or an intermediate compound are used. The perovskite layer is a polycrystalline layer. This means that the layer consists of grains with different lattice orientations and grain boundaries. As grain boundaries are surface entities in the bulk that facilitate defects, they can enhance the recombination of light-excited charge carriers. By increasing the grain size or decreasing the amount of grain boundary surface, the diffusion length for charge carriers could be increased from 1 micrometer up to more than 100 micrometers. However, some studies suggest that in some halide perovskite materials, the grain boundaries can act as conduction paths, which benefits the transport of the charge carriers in the absorber layer again. The exact role of and effects of the grain boundaries on the performance of halide perovskite solar cell is therefore still a subject of research. In the next video, we will discuss the different device structures of the halide perovskite solar cells.